Okay, so today we're going to start our last chapter of the school year, and that is chapter 11, and it's all about circles. And so today we're going to just learn some basic things about circles. Some you may already know, some that are new to you. Okay. So a circle is a set of all points that are equidistant from the center. Okay, so in this case, our center is C, right here. And all the points that are equidistant to the center create our circle. So that distance, which we always call a radius, okay, any point that's same distance away from the center creates our circle. So any point I draw this line out to, okay, all these lines are the same distance. And if I go a complete 360, that creates our circle. So again, we already know about a radius. In this case, we could name our radius a couple different ways here. In this case, we have AC is our radius, and it's a line segment. We could have BC or CB, okay, and we could have CD. It doesn't matter which order those letters are in, as long as it's one endpoint is the center and one endpoint is on the edge of the circle. Diameter, again, that's going all the way across. We've talked about that. So in this case, the only diameter we see in our picture would be AB. So again, this is going back to that first chapter this year of naming our segments. Okay, so be very careful. Line versus line segment versus rays. A chord. Okay, that is a new one for us. A chord is a segment whose endpoints are on the circle. Okay, so if you think about it, your diameter would be a chord. A and B, okay, are both endpoints on the circle. But a chord does not have to be the diameter. If we look at this example, EF would be a chord. It goes from endpoint to endpoint on a circle. And so does DA. So both of those could be endpoints as well. Again, a chord is a line segment, so we should not have arrows at the top of that at all. Just a little short line there to show that we go from those 2 points. Okay. Something else that's new is what we call a tangent. Tangent is a line that intersects a circle exactly 1 point. Okay. So that must mean that, one, it's a line. It goes on forever in both directions there. Okay, and it touches the circle at only 1 point, which would mean that it doesn't go on the inside of our circle. Because if it went on the inside, it would have to go out. So it would have 2 points. So the only line that we have right here would be this line right here, which is GH or HG. And then we have our line notation above that. And the last one, secant, a line that intersects a circle at 2 points. Again, this is a line, and the only line that we have that intersects at 2 points is EF. So it goes through the circle. EF, and again, put your arrows above that. So you do need to be careful there. That whole idea of a line versus a segment. So just be on the lookout for those and be careful with your notation. Some other important things. We have our first one is concentric circles. Okay, these are coplanar okay, me on the same plane, coplanar circles. If you notice it, you might see it in here, that they share the same center. So I have the big blue circle, the little red circle, both their centers are the black dot there in the middle. Congruent circles, I think you guys can take a guess what that means. We already know what the word congruent means, that they're the same. Okay, so circles that have the same radius. Okay, so if you have the same radius, then you are the same exact shape and size. So just like triangles, exact same shape and size. Okay, tangent circles. Okay, if you think back to above, tangent is that you touch at one point. So tangent circles are circles that touch or intersect at one point. Okay, and that's at exactly 1 point. So not they touch at least once, it's exactly 1 point. So circles that touch or intersect at 1 point. So we have two different types. We have external and internal. Okay, these are externally tangent because they intersect at 1 point and they are two separate circles. One is outside or here and one of the other one's on the other side. And then we have internally tangent, which means one circle is completely inside the other circle. Okay, so the red circle is completely inside the blue, but they only intersect at that 1 point. So you have those two different types of tangent, internally and externally. Today we're going to focus on some tangent theorems and do a little solving with that. Okay, so again, tangent means a line that intersects the circle at exactly 1 point. So we'll start with the first one. If a line is tangent to a circle, then it is perpendicular to the radius drawn to that point. So here is my tangent line. It touches it at 1 point. If I draw a radius to that point where it intersects, what happens is I create a right angle there. Okay. So what that means is the line K, remember, it's saying K is tangent, K is our line. K is perpendicular to QP. And that's going to form a right angle for us. Our next one, in a plane, if a line is perpendicular to a radius of a circle at its endpoint on the circle, then the line is tangent to the circle. So, if I have a circle in which the radius is drawn to a point where that line intersects the circle, and they are perpendicular, then that means that line is tangent to the circle. So if K is perpendicular to QP, then K is tangent to, now for circles, you're going to draw a circle with a little dot inside, and then you're going to say what the letter is in the center. So this means circle Q. Our next one, and again, you're going to use these to reference the bottom problems. If two segments from the same exterior point are tangent to a circle, they are congruent. So in this case, I have S, which is my exterior point, and the line SR is tangent to this circle, and the line ST is tangent to the circle. Thus, those line segments, SR and ST, are congruent. So if SR and SP are tangent to circle P, then SR and ST are congruent. Now we're going to use some of these theorems to try to solve a couple problems below. So the first problem says, is EF tangent to circle D? So here's EF. Is it tangent to the circle? Well, we think back to our theorems. If a line is tangent to the circle, then when I draw on the radius, DE, those are going to be perpendicular, which would mean we'd form a right angle. So really, when I look at this picture, I need to check, do I have a right triangle? If I do, then we're good. So we have 8 squared plus 15 squared equals 17 squared. Well, we know that's one of our Pythagorean triples, so yes, this is a right triangle. So yes, it is a right triangle. So that means angle DEF equals 90 degrees. Therefore, EF is tangent. Okay. It is tangent because it intersects at that one point, and it is perpendicular to the radius. Moving on to number 2. Okay, number 2, we look at this problem. We got to notice they gave us a little info down here. AB and DB are tangents to circle C. So AB, okay, and BD are tangents. Well, if they're both tangent, going to the same exterior point, if we go back up to one of our theorems, that means that AB and BD are congruent. So all I need to do is set 2x plus 2 equals 12. Do a little solving, subtract the 2 over, 2x equals 10, and divide to find x is 5. So again, we're just using the theorems that we learned above. Okay. Given BD and DY are tangents, okay, so we know BD, BY are tangents to circle A. We can go ahead and say that those are congruent. We know that DBY is 64 degrees. Okay. We know that this here is a right angle, and this is a right angle, so 90 and 90. They want us to find angle DAY. Okay, DAY. Well, you can do this a couple ways. You could draw in a triangle here and make some congruent triangles, or we could think that this is a four-sided shape, parallelogram. Not necessarily a parallelogram, but a quadrilateral. And we know that quadrilaterals have 360 degrees in them. So 360 minus 90 minus 90 minus 64. So we get 270, 180, and leaves us with 116 degrees. Okay. We actually look at this, we probably find out that we have a possibly looking at a kite there. Okay. So again, our last one here, number 4, given DF and DH are tangents to circles E and M. So D here kind of got covered up, but D's right there. Saying DF and DH are tangents to circles E and M. And we know that RDS is 50. So we know that this little one down, this angle down here is 50 degrees. They want us to find RMS, FEH, EHS, and DMR. Okay. So let's see if any of these are our right angles, because we now know that all of these are right angles. Well, RMS is this big one here. FEH is the other bigger angle here. EHS is that right angle down there, so we at least have our 90 then. And then DMR. So they actually want us to think about an angle that goes right there. Okay. So RMS. Well, let's think about this. Using the same logic as before, we know that this would have to, be angles that help these four-sided shapes, these quadrilaterals. So we focus in on this quadrilateral. We got, again, 360 minus 50 minus 90 minus 90. That's actually going to leave us a little bit more than last time. That's going to leave us with 130 for RMS. Well, if we extend this out, we have a similar shape there. It has the 50, the 90, the 90, so it's going to be left with, again, another 130. So there's your FEH. Now, the other way you can do this is think about, now we technically have some congruent triangles here. This triangle and this triangle would be congruent. So you could always think about that problem this way. So if we want to find DMR, which is right in here, we would see that this is a triangle, 180 degrees with a right angle, so take away 90. And then here we have this 50, which would make the small one 25. So minus 25. And you see that we're left with 65 degrees. Or you can think about it that it would be half of this big one, which was 130